Hello and welcome back. In this video, we'll continue looking at the slope and one of its more real-life sort of applications as a rate of change. So here's just a made-up graph describing some rent at a particular location. This is purely fictional. So we imagine that rent has sort of gone up over time. And in 1970, maybe the rent at some place was $400, and then it's gone up to $650 in 2020. So when we look at this, we might ask, well, what's the rate at which rent is increasing? Well, the rate it's increasing should be how much should be the change in price divided by the change in year. As in, how much did it go up in what time frame? So we can imagine, okay, so it's gone up from 400 to 650 here. So the change in price is going to be $250. But it took from the year 1970 to the year 2020. So this change took place over 50 years, which means that if we divide 250 by 50, we get 5. Now, we can't say the change was 5. I have to tell you, well, 5 what? In this case, this was $5 per year. So the rent increased from 1970 to 2020 $5 per year in this fictional place. So we can see that the change, a rate of change, how something is increasing versus how long it took to increase. This is just a slope. So when we want to calculate rates, or the rate of change of some amount, what we're actually doing is we're calculating slope. Now, this was nice because this was just a straight line, but when we look at more realistic data, it's not always going to be a straight line. But we could still somewhat talk about rates of changes. So for instance, if I still want to go from 1970 to 2020, what I can do is I can talk about the average rate of change. And the average rate of change, let me do this in red, is going to be the slope of this line there in red. So when we talk about averages, we're not worried about all of the messiness in between. We just want to know, where did we start and where did we finish? So on average, what was the, in this case, the change of price, or what was the rate of change in general? Now, this can seem a little bit silly at times, so I have I have an unlabeled graph here, but we can imagine that we take this point in time and we take this point in time. What happens when we look at the average rate of change over here? Well, we see that it goes up and up and up, and then it comes down and down and down. So overall, the amount that we've gone up balances the amount that we've come down, and we see that the rate of change here is going to be 0. This slope is 0. So we just have to be careful, and we have to remember that even though we may know what the average rate of change is between two locations is, we don't know what the actual rate of change is. It could have gone way up and way down, so they cancel out and we get an average of 0, or other crazy wackiness in between. So let's look at this as a function. The average rate of change of a function. So here's my function f, and the rate of change is going to be the difference in height divided by the difference in the x value. So again, here, let's say that I've got x1, and over here I've got x2. The height of the function at x1 is going to be f of x1. This is whatever you get when you plug in x1. The height at x2 is going to be whatever you get when you plug x2 into the function. This is what defines our function f. So then the rate of change is going to be the slope between these 2 points. Let me put this in red. So it's going to be the slope of this vertical line, or sorry, this straight line that connects these 2 points. And again, slope is going to be change in the y value, so rise divided by run. The change in the y value, the change in the height of the function, versus how long did it take to change. Even if it rose up a lot, if it took a long time to get there, the rate of change is going to be small. So let's apply this. Let's find the average rate of change in a function. This is meant to be x squared. So here's a graph of x squared, and we want to find the average rate of change from 0 to 1. So let me just graph this really quick. Here is 0, and when I plug 0 into x squared, I get 0 times 0, which is 0. Okay, so this makes sense. When I plug 1 into x squared, 1 times 1 is 1. So I want to find the average rate of change between these 2 points. So what I do is I will plug these in and figure out how much has it changed versus how far over did we go. So I want f of x2 minus f of x1 divided by x2 minus x1. So at 1, the height of the function is 1 squared. At 0, the height of the function is 0 squared. X2 is 1, x1 is 0. So if we go over 1, so we're going from 0 to 1, and then we're going from height 0 to height 1, so the rate of change is just the number 1. So when we look at this line, yes, the slope of that line going straight up there is 1. So how about from 1 to 2? Well, we already saw that 1 squared is 1, but now 2 squared is going to be 4. So this rate of change should be bigger, because we're going up faster. So let's see if this makes sense. F of x squared minus f of x1 divided by, shouldn't call this x squared, this is x2 minus x1. X squared is something completely different. When I plug in my values, I'll get 2 squared minus 1 squared over 2 minus 1. So again, as we go from 2 to 1, from 1 to 2, we've gone over 1 step, but the height of the function has gone from height 1 to height 4, so it's gone up 3. So the slope here, the average rate of change, is going to be 3. It's going up a lot faster. And let's look at one more of these. So we're going from -2 to 0. So let's come back up and graph this. So we're going from -2. So at -2, -2 squared is going to be 4. And we're going all the way to 0 now. Oops. If I could draw. And the idea here is that this line should look maybe a little bit steeper than this first one, but maybe not quite as steep as this second one. So we'll see if this makes sense. But again, here we should be going down, and by going down, I mean we should have a negative slope. So let's check it out. We'll take f of x2 minus f of x1 all over x2 minus x1. F of x2, so x2 is going to be 0, so we'll have 0 squared minus x1 squared, which is going to be -2 squared, all over x2 minus x1. Now, we have a few negative signs, so we'll have to be careful. Going from -2 to 0, well, it's 2 steps to get over. And 0 minus a -2, minus a -2, the negative signs cancel, and you just get 2. On top, we've got 0 squared minus -2 squared. Well, negative 2 squared is 4, and 0 minus 4 is negative 4. And negative 4 divided by 2 is, in fact, negative 2. And this makes sense. We have a negative slope. We're going down. From this point to this point, we are going down. So this is how you calculate average rate of change of a function. Sometimes the formula for the function isn't given to us, and we just have a graph. This we'll just have to estimate a few things. So let's try to find the average rate of change from 1 hour to 3 hours. So when we look at this, we've got time in hours, and then we've got a concentration of a drug. So I think this graph comes from the book, and it's essentially after you give a patient some drugs, the drugs will take a little bit of time to make it through the system so that the concentration is at the highest, and then the body will start to use the drugs to do whatever, to feel better. And as they get used up, they decrease. So the average rate of change from 1 hour to 3 hours. So at 1 hour, we're here. So this point is going to be 1.03. And then from 3 hours, so 3 hours we're at the peak up here. This is going to be 3.05. So again, we want to know the difference in height. So this will be we're at this height. So the difference, we have climbed 0.02 milligrams per milliliter, but we also rose from 1 to 3. So it took 2 hours for this to happen. So this will be 0.01. And we should also include some units in here. So what changed? The concentration, so milligrams per 100 milliliters. So it went up, because this is a positive number, it went up by 0.01 milligrams per 100 milliliters per hour. It took 2 hours to climb 2 milligrams per 100 milliliters. So on average, it was 0.01 milligram per 100 milliliters. And then we can look at the average rate of change from 3 hours to 7 hours. So from 3 hours, we're at the peak. Over here at 7, we're at, so again, 7 hours, and this will be 0.02. So then we can find the average rate of change here. So we ended up at 0.02, but we started at 0.05, which means that we fell by 0.03 milligrams per 100 milliliters. But it took from hour 3 to hour 7 to get there. So it took 4 hours for this to take effect. And if we divide this out, this will be negative 0.075. So it fell by this much because we have a negative number, and then the units will be how much it rose or fell, again, per hour. Okay, so this is quite useful to be able to estimate rates of change. We can also draw these straight lines in here to see exactly what numbers we're estimating. It's the slope of this line versus the slope of this line for the second.